Welcome back to the Rundown Lab, where we break down and fact check the biggest health podcasts. We know your time is valuable, but when you can, we always recommend catching the full episode. Links are in the description. Here's an interesting question. What actually happens in your brain when you learn something new? And what if the same basic algorithm that teaches a honeybee where to find nectar is also running in your head right now, helping you decide whether to keep listening to this? That's the kind of big picture thinking that came up in a recent Huberman Lab episode featuring Dr. Montague, a neuroscientist who spent decades studying how dopamine and other brain chemicals shape our decisions. The conversation covered a lot of ground, from Parkinson's disease to artificial intelligence to why your phone might be making you dumber just by being in the room. So let's dig into what the science actually says. First, some things they really nailed. The core idea that dopamine fluctuations, both increases and decreases, control learning, that's solid neuroscience. This is the reward prediction error theory, established by Wolfram Schultz and colleagues. When something turns out better than you expected, dopamine neurons fire more. When it's worse than expected, they fire less. Both directions drive learning. It's a beautiful system. The discussion of computational models was also on point. The Rescorla-Wagner model from 1972 was correctly identified as foundational to how we understand associative learning. And the connection between temporal difference learning algorithms and what eventually powered AlphaGo, the program that beat the world champion at Go? That's a legitimate link, though AlphaGo actually used TD learning as one component among several techniques, not as its sole approach. There was also a striking claim that anorexia nervosa is the most dangerous and deadly psychiatric illness. That's accurate and worth emphasizing. Meta-analyses consistently show anorexia has the highest mortality rate among psychiatric disorders, with standardized mortality ratios 5 to 10 times that of the general population. And the discussion of that Israeli study on judges making parole decisions? The study exists. It's real. It was published in PNAS in 2011. And it did find that favorable decisions dropped dramatically before meal breaks. Though I should note that study has faced significant methodological criticism. Later analyses suggest case scheduling, not just hunger, might explain the pattern. Now let's get into where things got more complicated. Several claims were in the right neighborhood, but simplified complex biology in ways that could mislead you. Take the claim about Parkinson's disease and losing 70 to 75% of dopamine neurons by the time symptoms appear. The spirit of this is right, and it's an important point about how much damage occurs before we even notice. But the numbers are a bit off. The commonly cited figures are actually 50 to 70% loss of dopamine neurons in the substantia nigra, with 70 to 80% depletion of dopamine in the striatum, which is where those neurons project. That distinction between neuron loss and dopamine depletion matters for understanding the disease. The specific claim about having 80,000 dopamine neurons per side, totaling 160,000? Current estimates actually suggest 400,000 to 600,000 dopamine neurons in the substantia nigra alone. That's a significant difference. There was also an interesting claim that honeybees use the same learning algorithm, but with octopamine instead of dopamine. This is partially right. Octopamine is important for appetitive learning in insects. But here's what's fascinating. Recent research shows dopamine actually plays significant roles in insect learning too, particularly for aversive conditioning. The picture is more complex than a simple swap of one chemical for another. The opponent process idea, that dopamine and serotonin always move in opposite directions, is an influential theoretical framework from Daw, Kakade, and Diane's work in 2002. But stating they always move in strict opposition oversimplifies their relationship. These systems can act independently, and their interactions vary by brain region, timescale, and behavioral context. Now for the red flags. Claims that were misleading or couldn't be verified. There was a claim that hungry rodents show dopamine encoding punishment prediction errors rather than reward prediction errors. Research does show that hunger states modulate how dopamine neurons respond to food cues, but characterizing this as flipping to punishment prediction errors misrepresents what the studies actually found. Hunger changes how valuable food is. It doesn't flip dopamine's fundamental function. And there were a couple of specific claims, including one about a 40% difference in some serotonin-dopamine interaction study, and another about work by a researcher whose name I couldn't clearly identify, that simply couldn't be verified. The specific sources couldn't be located in scientific databases. That doesn't mean they're wrong, but it means we can't confirm them. The description of SSRIs increasing serotonin that then gets used at dopamine synapses to reduce reward was also oversimplified. Serotonin-dopamine interactions are real and complex, but the phrase "gets used at dopamine synapses" makes a complicated, still debated mechanism sound more straightforward than it is. So what's the bottom line? This was a substantive conversation with a researcher who clearly knows the field deeply. The foundational concepts about reward prediction errors, temporal difference learning, and computational approaches to understanding the brain were presented accurately. Where things got shaky was in specific numbers and in oversimplified descriptions of how brain chemicals interact. The key takeaway? Dopamine really is central to learning and motivation, and the computational framework for understanding it is one of neuroscience's genuine success stories. But the brain is messier than any simple model. Serotonin and dopamine don't just seesaw up and down in opposition. They have complex, context-dependent relationships we're still figuring out. When you hear claims with very specific numbers or very clean mechanisms, that's often where the science is actually more uncertain than the confident delivery suggests.